Welcome back. Today we'll be looking at limits at infinity. The goals of this video will be to find limits at infinity and also to determine if a function has a horizontal asymptote. We sometimes need to determine limits when the inputs get larger and larger without bound, that is when they approach infinity. Infinite limits tell us something about the end behavior of a function on an infinite interval. Remember that end behavior from your college algebra days describes how the graph behaves, either moving to the right or moving to the left. Infinite limits are expressed as follows: the limit as x approaches positive infinity of f of x, or the limit as x approaches negative infinity of f of x. Let's take a look at an important theorem used in determining the values of limits at infinity. If r is a positive rational number and c is any real number, then the limit as x approaches infinity of c divided by x to the power of r is equal to 0, and the limit as x approaches negative infinity of c divided by x to the power of r is equal to 0. Essentially what's happening here, we have a fixed numerator and we have an either increasing denominator that will approach 0, or if we have a fixed numerator and a decreasing denominator, that will also approach 0. Let's take a look at why these are true. Let's consider the function 2 divided by x cubed graphed here, and let's see if we can determine the limit of this as x approaches positive infinity. From a previous video, we know that we can analyze this either using a t-table or the graph. Let's take a look at the t-table first. As x approaches positive infinity, I've chose values of x that start at 1 and increase by powers of 10, and you can easily see that the y values are getting smaller and smaller, approaching 0. So this limit would be equal to 0. Graphically, as we approach positive infinity, we will be moving to the right, and you can quickly see that the y values, as we move to the right, are approaching a y value of 0. The second limit, as x approaches negative infinity, I'm starting at -1 and decreasing all the way to -1000. We can quickly see that the y values are approaching 0, this time from the negative side, but still approaching 0. Graphically, as we approach negative infinity, we would be moving to the left, and again you can see that the y values are approaching 0, but from the negative side this time. Another important use of limits at infinity is to determine if a function has a horizontal asymptote. The line y equals L is a horizontal asymptote of the graph if either of these infinite limits are equal to L. The general guidelines for finding limits at infinity of rational functions are as follows. Divide each term in the argument by the highest power of x in the denominator. Find the limit at infinity in the new form. Now there are some shortcut rules for finding limits at infinity of rational functions. Let's take a quick look at this and then we'll look at some examples. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. Essentially what's happening here, we have a rational function where the denominator is increasing faster than the numerator, and that limit will equal 0. Number 2, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. Again, we'll look at this in just a moment. And lastly, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So essentially what's happening here is the numerator is growing faster than the denominator, therefore it's going to approach either positive or negative infinity. Okay, let's look at this in practice. We want to find the following limits. The limit as x approaches infinity of the function 1 divided by x plus 3. Here's the graph, but let's take a look at the theorem that we just discussed. We know from the properties of limits that this is equal to the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 3. Well, here we have a limit where the numerator is fixed, the denominator is increasing, so this limit is going to equal 0 plus the limit as x approaches infinity of 3. Well, there's not even an x in this argument, therefore this limit is going to equal 3. Graphically, if we take a look at this function And since we're approaching positive infinity, if we go to the right, we can easily see that the graph is approaching the y value of positive 3. And as mentioned before, we could also conclude from this graph and this limit that there is a horizontal asymptote at y equals 3. Now this is not the question here, but that is an important connection to make. The limit as x approaches negative infinity of 2x plus 5 divided by the quantity x minus 1. Now the general guideline is to divide by the highest power of x in the denominator. So let's go ahead and do that. So the highest power of x in the denominator is x, so I'm going to divide every term by x and then simplify as much as I can. When we do this, it should be easier to determine this limit. These x's simplify, so we would have 2 plus 5 divided by x over, this simplifies, 1 plus 1 divided by x. Again, using that theorem we just discussed, 2 is not affected by x, this would approach 0. 1 is not affected by x, this would approach 0. Therefore our limit would be equal to positive 2. Graphically, as we approach negative infinity, we will be moving to the left on the function. So we move to the left, you can see the y values here are approaching positive 2, which verifies our limit. Lastly, the shortcut rule says that since the degree of the numerator and denominator are equal to 1, the limit is equal to the ratio of the leading coefficients, which would be 2 over 1, which we found as 2. Let's consider this limit now. Let's take a look at the graph first this time. As we approach positive infinity, we're moving to the right. So if we start on the function and move to the right, you can kind of see that the graph is moving downward. Looks like it is going to approach 0, but let's verify this with some other techniques. Again, the rule says to divide by the highest power of x in the denominator. So in this case, we would divide every term by x to the third. So we have 3x squared divided by x to the third minus 5x divided by x to the third, and so on. We're going to simplify this. This would be 3 divided by x. This would be 5 divided by x squared. This would be 1, and this would be plus 7, and this would be 7 divided by x to the third. Again, taking the limit of each of these terms individually, this approaches 0, this approaches 0, that would stay at 1, this would approach 0. Therefore, we could conclude that this limit would be equal to 0 divided by 1, or of course just 0. It's quite a bit of work, but this does verify what we were looking at graphically. Lastly, using the shortcut rule, since the degree of the numerator is less than the degree of the denominator is increasing faster, therefore this limit would equal 0. Okay, let's take a look at one more. Now this one, I'm just going to look at it graphically and then take the shortcut rule. The limit as x approaches infinity, we're moving to the right on this function. If I move to the right, the function is going up indefinitely. Therefore, this limit would be equal to infinity, which of course does not exist. Another way to verify this using some algebra, this function can be simplified. There's a common factor of x in the numerator. So if we factored this, we could see that this factor of x simplifies. Therefore, this limit is equal to the limit of 2x minus 5, which obviously again verifies this approaches positive infinity. I hope that helps. Thank you and have a wonderful day.